Good morning to all. Myself, Lakshmi Narasimha. I am going to explain about dynamic programming. In this tutorial, we are going to cover the following subtopics. That is, what is a dynamic programming, and how many ways we can implement the dynamic programming, and applications of a dynamic programming. Now, now let's understand about the dynamic programming. Dynamic programming is a general algorithm technique which is used to solve the recurrences with overlapping subproblems. What is an overlapping subproblems? If we are given with a problem, generally we will divide it into subproblems in order to get the solution. Then, if I take a subproblem of a given main problem, that subproblem is being executed or recomputed again and again, then it is known as overlapping subproblem. Now, some of the characteristics that needs to be acquired by a problem in order to use a dynamic programming is simple subproblems. That is, the given problem should be divided into multiple smaller subproblems. And next one is an optimal substructure of the solution. That is, each of the subproblem should contain an optimal solution among the pool of solutions. And the last one is the overlapping subproblems, what we have discussed earlier. That is, an subproblem is being executed or recomputed again and again. Thus, this can be overcome by using a dynamic programming. Now let's understand the dynamic programming with an example, that is a Fibonacci series. Here we can see that a fib of 5 is a calculator where it is divided into two types, fib 4 and fib 3, and 4 again divided into 3 and 2, 3 again 2 and 1. If we observe clearly, here fib of 2 is already completed, that is one of the subproblem, and again it is executed in the fib of 4 to find the fib of 2. That is, the same problem is executed again and again. This is one of the drawback. So what dynamic programming does is, when an problem is divided into subproblems, when it is executed and stored in an table, whenever the same subproblem is being executed, then it uses that value from the table instead of recomputing it. From this way, we can overcome the overlapping subproblems. Previous slides, we have understood what is an academic program and how it solves the overlapping subproblem issue. Now, from this slide, we will understand how many approaches are present in order to deal with the dynamic programming. One is top-down approach, another one is bottom-up approach. Top-down approach is chooses a recursive technique, whereas a bottom-up approach uses an iterative approach. Both of them do the same work, but when a problem was given to them, it first initially divides the problem into many subproblems and goes to each edge cases and solves the each problem and store it in an table or an matrix. Whenever the same subproblem again occurs again, then instead of re-executing it, it uses the value stored in the table or a matrix in order to solve the problem instead of re-executing it or recomputing it. From this slide, we will know the applications of the dynamic programming. There are many number of applications of dynamic programming. Among them, three are the major parts of the dynamic programming. One is knapsack problem, Warshall's algorithm, and Floyd's algorithm. Suppose if we take a knapsack problem, let us assume an situation where a thief entered a house which is inside a town. Now, the thief contains a bag of weight 15 kgs, and the items present in the home are surrounded by this bag. Now, the thief can carry the items inside the bag, but the items should not exceed the weight of that bag, that is the 15 kgs, and the items what he included should give him maximum profit. That is the knapsack problem. Whereas Warshall's algorithm is an algorithm which tells us whether there is a path exists between the two nodes. Suppose if I take a node ij, it checks whether there is an path between ij or is there any intermediate node that connects ij. This is also known as transitive closure. And the final Floyd's algorithm shows that it finds the shortest distance from a particular node to all other nodes. Suppose we have a node A, B, C, D. and it checks that whether there is a path exists, whether there is a path exists between A, B, AC, and AD, and finds the shortest among them. Similarly, it takes the B node and checks the distance between BA, BC, BD, and finds the shortest. Like that, it does for each and every of the node. These are the applications of dynamic programming. Now let's deep dive into the applications of a dynamic programming by using the knapsack problem 01. Now let's start with the first application of a dynamic programming, that is a knapsack problem. Knapsack problem contains different types, that is a 0-1 knapsack or a fractional knapsack. First of all, what is a knapsack problem? Suppose we'll take a situation where a thief entered into a house. He had a bag with a weight M. In this case, let it be a 20 kgs. Now he is surrounded with the items present in the house. Each of the items in the house contains its own weight and a own profit. Now, the aim of the thief is to select the items in such a way that the sum of items what he has selected should not exceed the weight of that bag, and he need to get the maximum profit. That is, it should not exceed the weight of the bag, but he need to get the maximum profit. If we see into the definition or the problem statement, given there are n items, a house can contain n items, each with a weight of WA. Each of them contains a weight of their own. Suppose here 3 kgs, 6 kgs, 1 kg, 2 kg. And each of them contains their own value. That is the profit or the cost of by which with what the owner has bought. Now we need to determine the items so that I can include it in the bag, and it should not exceed the weight of the bag and I should get the maximum profit. Now we understood what a knapsack problem is. Now let's understand the types of knapsack problem. We mainly contain two types of knapsack problems. One is a 0-1 knapsack problem, another one is the fractional knapsack problem. 0-1 knapsack problem is a knapsack problem in which either I'll take a complete item inside the surrounded by the bag, or I won't take that item at all. Suppose in this case, if I take a 3 kg block, I'll take complete 3 kgs and place it into the bag, or I won't take 3 kgs completely and I'll keep the bag like that only. But in fractional, what happens is if there is a 3 kg block, I can take a fraction of it. That is, I can take a 1/4 or a 2 kgs or 2 kgs among the 3 kg block and place it in the bag. This is the difference between the 0-1 knapsack and a fractional knapsack. Now we understood what is a knapsack problem, what are the types of knapsack problem. In next slides, we will know about the knapsack 0-1 problem clearly with their problem algorithm, statements, and with an example. Now let's clearly understand about the 0-1 knapsack problem with an example. We are given with three items of weight 111 and of the profit 10, 20, 30, and the capacity of the bag is given as a 2. Now we are given with an binary tree where it represents that the right side of the tree or the right child represents that we are including the item, whereas the left part or the left child represents that we are not including that item. So now we have got to understand that we mainly contains two of the cases, that is adding an item or we are not considering as an item to be added into the bag, that is adding or not adding. Now we will see the cases of when we should add and when we should not add the item. Where we should not add the item or an given object when the weight of that object is more than the capacity of the bag. Suppose here if I have the weights as 111. Now each of the weight is less than the capacity of the bag, so that I can add them into the bag. But if there is a weight with a 2 or 3, there is a item with a weight 3. Now 3 is greater than the capacity of the bag, so that I won't add that item inside the bag. Rather, I will exclude it. Now, when we exclude that particular item, no new profit will be added to the bag, so that the state will be same, but the number of objects available will be decreased. So on the left part, we could see that we got 2 comma 2. As the number of objects decrease, so it became an 2, and the weight of the bag will be remaining same, that is a 2. Now we will look into the including case, that is k of 2 comma 1. Here now we need to choose two cases in the including also, that is checking whether the current profit is more or the profit that is resulted by adding the new item is more. Now, when we add the item, the number of objects will be available will be decreased by one, and the capacity of the bag also will be decreased. We will add the profit also. So we should take the maximum of the new profit and the old profit. Based on this, we will write the or construct the table so that the subproblems will be stored and not recalculated or executed whenever it is needed. In previous slides, we have seen that we either need to include or exclude a given item, but we are not storing the result inside any table or a matrix in order to reuse it when the same subproblem occurred. So now we will construct a table and store the result of that particular subproblem so that I can reuse it when the same subproblem occurred again. The main goal is to find b n comma w, where n is the number of items and w is the maximum weight of the knapsack. If we see the recursive formula below, it is similar to the formula what we had discussed before. That is, if the weight of the current given object or an item is greater than the capacity of a bag, then we will not add that particular item inside the matrix. But if the weight of the object or an item is less than the capacity of the bag, we need to check for the two conditions. That is, whether the previous profit is more or the new profit which is produced by adding the item is more. That's what here it was shown. That is maximum of b k minus 1 comma w, that is the previous profit, or b of k minus 1 comma w minus wk, that is the profit which we got after adding the new item. Hence, by using this, we can construct the table and store the results and use it whenever the same problem occurred. Now let's understand the 0 1 knapsack algorithm with an example and the code snippets given below. The main motive of the knapsack 0 1 problem is to provide the number of items that can be placed in the bag of a capacity M and the maximum profit that is provided by adding those items. So we during this process, the knapsack will provide a matrix where it contains rows and columns. Rows represents the number of items and the columns represents the weight or the capacity of the bag. Now, initially, the first row and the first column is set to zeros because if we take the zeroth row, that is the number of items as zero, even if you increase the number of back to weight capacity also, you cannot add items because since the number of items are zero, we can't add the items inside the bag even if it is how much capacity it was. So that the zeroth row will be 0. Now if we take the zeroth column, even if the weight of the bag is 0, and if we increase the number of items, we can't add into the bag since the capacity of the bag is 0. This is why the zeroth row and the zeroth column will be sent to 0. Now if we take the example given below, we are given and 4 items with their weights and corresponding values. 2 comma 3, 3 comma 4, 4 comma 5, and 5 comma 6. The first item that is the first row, that is number of items is equal to 1 and the bag capacity is 2, then only I can place the profit as a 3. It means item 1 can be placed inside the bag of a capacity 2 only. Till then I can't place the other item now. So that 1 comma 1 is 0 since the capacity is 1. At capacity 1 we don't have any items to be placed. So that at capacity 2 I have added the first item. So I have placed the profit inside the 1 comma 2. Similarly 1 comma 3 1 comma 4 and 1 comma 5 is also 3 because I have only that particular item and I don't have any second item or a third item at that point of time so that I can fill the bag only with that particular item. Now if I go for the third row, that is two items available, here we should check two cases. One is availability of the items and which item you are adding. If you check for we have two items available. Now since till the bag weight capacity is equal to 2, you can't add more items. So that at a bag capacity is equal to 2, I can add only first item. Among two items, I can add only first item, that is 3. Now, in order to add a second item, following conditions need to be satisfied. Those are, that is, it should contain the same weight as the before, or it should be decreased. That is, either we need to include that item or we should exclude that item. That is, in case of 2 comma 3, it should be same state, that is 3, or we should include that item, or go up and go back to the 3 times, because the weight of the second item is a 3. So go to 3 times, 3 to 3, that is 3 to 2, 2 to 1, and 1 to 0. We got 0. Hence 0 plus the profit of second one is 4. 0 plus 4 comma previous state, that is 3. Among those both, which one is maximum? That is 4. That is, the profit 4 is maximum than 3. Therefore I have added a 4 inside of the table. And similarly for the next one, I want 2 comma 4. The previous state is 3, but so 3, or go back to 3 times, 1, 4 to 3, 3 to 2, and again 2 to 1, 0. So a 0 plus the profit of second one, that is 4. 3 comma 0 plus 4, maximum is 4, so I have written as 4. And similarly, when I want a 2 comma 5, now the previous data, that is 3, or go back to 3 times of, that is the weight of that particular item, that is 2. 1, 4, 5 to 4, 4 to 3, and 3 to 2, that is 3, plus the profit of second one, that is 4. 4 plus 3, how much? 7. So 7 will be added inside that, because 7 comma 3, which is maximum 7, so that we will add 7. Like this, we will compute each of them and go till last, and this last box provides the maximum profit. Now we got the maximum profit. Now we need to get what are the items that needs to be added. Now we should check. Suppose here 7 is there. In this, how did we got this 7 here? Check the previous state. Previous state and the current state is 7. Same. So there is no change. Check the previous state. Previous state and this state is same. So I didn't get from the previous state also. So check the previous state. If I check here 7 and 3, there is a change. Means I got a 7 here because the previous state 3, or 3 plus 4, we have seen, right? We went 3 positions back, added a 3 with the profit, that is 3 plus 4, that's why we got 7 here. Means because of item 1, I got 7 as a profit, so that we should include item 1. And again we'll go back, that is 3 and 0. If you check, there is a change. Now you check why I got 3 here. Why I got 3 here? Because go here. If you see, now go here, here. Yeah, I got 3 here because of adding that second item bag weight capacity to this, so that at this point of time we can add this 0 item and the 1 item, because of adding 0th item and the 1 item, there is a change in the profits. So the maximum profit will be given by the last column, last value in the matrix or the table, and the items that needs to be included can be produced by using the backtracking technique. This is about the knapsack problem. Next slide, we will know about the next application of dynamic programming. Now let's start with the second application of the dynamic programming, that is a Warshall's algorithm. The main motive of the Warshall's algorithm is to check whether the path exists between the two given nodes. Suppose if I take the two nodes I and j, it checks whether the path is present between them, whether it may be a direct path or then is an indirect path by using another node. Suppose if you take the figure shown here, it may contain a direct path from I comma j, or it may contain an indirect path from I to j with the help of k. The formula also says the same thing, that is r of k I comma j is equal to r of k minus 1 I comma j, that is the direct path from I to j, or r of k minus 1 I comma k and r of k minus 1 k comma j, that is the distance from I to k and from k to j. This is also known as the transitive closure, and the output of a Warshall's algorithm gives the transitive closure of a given graph. If we look into the algorithm, it takes an adjacency matrix and provides the output as an transitive closure of that given graph. We will take the adjacency matrix and iterate through each of them and checks whether there is an path exists from the particular nodes to remaining nodes by with whether it may be direct or indirect. This is known as a Warshall's algorithm. Let's understand it with an example in the next slide. Now let's understand Marshall's algorithm with an example. We are given with an directed graph with four vertices, which are connected by the directed edges. Now we need to take the adjacency matrix, and by using the adjacency matrix, we need to find the next state, that is R1. To find the next state, we will take the zeroth row and the zeroth column, that is eighth row and the eighth column, as the same in R1 also. Now we need to find the remaining items, and we need to keep the ones present in the R of 0 as in the same position in R1 also. We should just find the values of zeros. Okay, now if I want a b comma b in R1, now I should take the current value 0 or multiplication of b comma a and a comma b, that is 0 into 1, 0 or 0 into 1, the value is 0, hence I got a 0 here. Now if I want b comma c, I need to take the current value 0 or b comma a and then a comma c, which is 0 and 0. The thing is here b is acting as an intermediate between a and c. Now if I want C comma B value, I need to take current value 0 and C comma A, multiplication of C comma A and C comma B, that is 0 into 1, 0 or 0 into 1, again the value is 0. After completing R1, now we need to get R2, that is the next state, by using R1. By for getting R2, I will place the bth row and the bth column, that is the second row and the second column, as the same in R2. Now if I want a comma a, now if I want a comma a, I should take the current state, that is 0 or b comma a into a comma b, 0 into 1, the value is 0 again. If I want a comma c, the value of that current a comma c value, that is 0, or the multiplication of a comma b with b comma c, that is 1 into 0, that is 0 again. If I want the value a comma d, the current value is 0, or the multiplication of a comma b and b comma d, that is 1 into 1, hence I got a 1 in the R2. In this way we will construct the next state for all the four nodes, and the last one provides the transitive closure, that is the whether the path exists between the a and b, a and c, a and d, etc., whether it may be direct or indirect. In this way we'll get the transitive closure, and the Warshall algorithm uses dynamic programming to get whether the path exists between two nodes, whether it may be direct or indirect. Now let's understand the third application of a dynamic programming, that is the Floyd's algorithm. The main motive of the Floyd's algorithm is to find the all pair shortest path. In the name only, it says that all pair shortest path. That is, it finds the shortest path from the given node to all other nodes. Suppose in this graph, if you see, it takes a 0 and finds the shortest path between 0, 1, 0, 2, 0, 3, and after completing 0, it takes a 1 and it goes and finds a shortest path between 0, 1, 1, 0, 1, 2, 1, 3, and after completing 1, it goes to 2 and finds the shortest path between 0, 1, 0, 2, 0, 2, 1, 2, 3, and it completes till 3, like that. But if you take the Dijkstra's, the difference is that it takes only a single source node, suppose 0, and finds the shortest path to it from other nodes 0, 1, 0, 2, 0, 3. It won't calculate a 1 to shortest paths to 1 and 2, only calculates for the single source one. And the another distance difference between the Floyd's and the Dijkstra's is that the Floyd's can contain the negative edges, that is the weights of the edges can be negative, whereas in Dijkstra's the weights of the graphs should not be negative, and in Floyd's we should not contain negative cycle, that is the sum of all the edges should not be negative. These are the key differences between the Floyd's and Dijkstra's. When we look into the Floyd's algorithm, it takes the weighted matrix, which I will explain how to write the weighted matrix in the next slide, the weighted matrix, and then provides the matrix with which shows the all pair shortest path from the current node to all other nodes. It traverses through the matrix and finds that whether the current distance between I and j is shortest, or the distance from I and j through an intermediate is smaller. That is, if I have two nodes, 1 and 2, is the direct path 1 and 2 is smaller, or the distance from 1 to 3 and 3 to 2, this indirect path is smaller, or 1 to 2 direct path is smaller. Based on that, minimum path will be taken. This is about the Floyd's algorithm. In next slide we will learn about how to write the weight matrix for an given graph. First, let's learn how to write the weighted matrix. It is similar to adjacency matrix, but instead of writing ones and zeros, here we will write the weights of each edges. Suppose if I take a b comma a, the weight of the edge is 2. So I write a b comma a as a 2 in the weight matrix. And since there are no loops, that is a to a or b to a or b to b, like that, we will write them as zeros. Next one is when there is no edge present. Suppose a comma b there is no edge present. In those cases, we'll write it as infinity or any large number. And hence we have learned how to write the weight matrix. Now let's learn how to solve the weight matrix and get the shortest path from each node to other node by using Floyd's algorithm. Floyd's algorithm is also similar to that of Warshall's algorithm. So first we'll take the weighted matrix, yeah, which and represent it as a d of 0, and by using d of 0 we'll find the d of 1. In d of 1 we will place the 0th row and the 0th column as the same of the d of 0, that is 8th row and the 8th column. Now if I want to find the b comma b, I'll take the current distance, that is 0 comma and the intermediate distance, that is 2 plus infinity, that is b of a plus a of b, that is 2 plus infinity. 0 comma 2 plus infinity, among these which is a minimum, that is 0 is minimum, so that I'll write it as 0. Suppose if I take if I want a b comma if I want b comma c, now the current state is infinity, comma b comma a plus a comma c, that is 2 plus 3, that is 5. Now the minimum of infinity comma 5 is 5, so I got here 5. If I take the third state, that is b comma d, which is infinity, the current state infinity, comma b comma a plus a comma d, that is 2 plus infinity. Hence infinity comma infinity, minimum will be infinity, so I'll write it as infinity. If there is any value present, suppose here 7 1, we should not change those values, we should write as it is in a d of 1 only. Whenever we get the zeros or infinities, then only we should go for the Floyd's algorithm formula. In other cases, we should write similarly what in the similar question, what is present in d of 0, we should write same in the d of 1 also. Now, after calculating d of 1, in the same way, calculate d of 2, d of 3, d of 4, and the d of 4 provides the shortest distance from A to all other edges. Suppose if you take d of 4, shortest distance between A and A is 0, shortest distance between A and B is 10, and the shortest distance between A and C is 3, and A and D is 4. Like that, B and A is 2, B and B is 0, like that, so on. From this, we can understand that how TP is used to find the shortest path from a given node to all other nodes. And this is the end of the video. And thank